This is the end of factorials, and we're going to go on to binomial coefficients. OK, so kind of in principle, you know, binomial coefficients, n choose k, it's like n factorial over k factorial times, in the denominator, n minus k factorial. And you're like, well, we just got Stirling's formula that gives us an incredibly precise formula for factorial, so just plug it in, and you're done. And that's sort of true. And we'll, in fact, do exactly that at the end of class. There's two catches, though. One catch is like it's more annoying because there's two parameters in a binomial coefficient, n and k. And so somehow the asymptotics is more confusing because it depends sort of how k depends on n. Like, is k like a constant, like 5? Is k like square root n? Is k like 0.3n? Somehow the form of the asymptotics changes. And the other reason we're going to save plugging in Stirling's formula to the end is because we're going to follow this strategy of just starting with the most naive possible bounds. So let us, good. Let's start. So what does n choose k? Well, as you know, it's n factorial over k factorial times n minus k factorial. And usually, psychologically, you should think of k as kind of small. And therefore, like this is, I mean, most times. So this is smallish. But n minus k is kind of like n. So this has like many more factors than this one. So it's good to, most of the time, to like cancel all these factors with these ones up here and only leave k terms on the top and k terms on the bottom. What I'm saying is just that this is equal to n times n minus 1 times n minus 2. There's k terms up here. And the denominator also has k terms. It's k factorial, but I'll just write k factorial. I mean k times k minus 1 times dot, dot, dot. OK, so this is an easier way to think about it. And as I said, the way you want to treat this sort of depends on how big or small k is. For example, like imagine k is 3. OK, let's say k is 3. Well, then n choose 3 is n, n minus 1, n minus 2 over, well, 3 factorial is 6. OK, and you know, this is asymptotic to n cubed over 6. And that's it. You're done. And that's true in general. So for quote unquote small k, n choose k is approximately n to the k over k factorial. Where remember this approximately sign has no meaning. It's just, you know, it's heuristically around this. I mean, and we'll have to say better if we want to. You know, if k is really like 1, 2, 3, 4, 5, 10, then now you're done. Like this, if it's 10, it's n to the 10 over, I don't know what 10 factorial is, but it's some number. Good. But let's do this more accurately. So more accurately, OK, this expression, well, again, what you should do, just imagine there's like 10 terms up here in the numerator, and you're trying to make it look like n to the 10th over 10 factorial. Again, what you should do is like factor out the term that you think is the real term and leave all the rest as like the junk. So you would do it like this. You would say this equals n to the k in general over k factorial. And we're going to factor it out now. And what are we left with? We're left with 1 minus 1 over n. That's, I mean, we're going to factor an n out of n and get 1. We're going to factor an n out of n minus 1 and get 1 minus 1 over n. We're going to factor an n out of n minus 2 and get 1 minus 2 over n, and so forth. So we're going to end up by factoring an n out of n minus k plus 1 and get 1 minus k minus 1 over n. So that's exact. And now you may see why I bothered to repeat the birthday paradox thing at the beginning, because it's exactly the same. We have this product here as like our junk. So let me not belabor it, but this piece, this is like, again, I'll write a little funny. This is like 1 minus k squared over 2n, basically, right? I mean, we saw you can convert these all to e to those, multiply them, add up these quantities, convert it back. OK, so these things add, and you get minus 1 over n times 1 plus 2 plus 3 up to k, which is like k squared over 2. OK, but now I've gone back to being a little heuristic here. But this is if k is small, because all these approximations where this is approximately the same as e to the minus k over n is only true if k over n is small. And in fact, if you work through it a bit more, like this approximation is only accurate if this thing, you're trying to imagine that this is the overall error term, if like this thing is small, which is only small if like k is a lot smaller than root n. OK, so what I'd like to just say, I'll conclude it over here. Sorry for doing this board a little in a weird order. But the following is true. N choose k is asymptotic to n to the k over k factorial, provided k, if you think about it as like a function of n, is little o of root n. Which is to say that like this is asymptotically small. Was there a question? OK, so if you see something like n choose 2 or n choose 10 or n choose n to the point 1, then this bound is asymptotically accurate. Now, what if k is not smaller than root n? Turns out that it's actually kind of tricky and interesting. So for most of the rest of the class, I'm actually going to jump up to worrying about the case when k is proportional to n. So k is like maybe 0.1 times n. And part of the reason for that is, as I said, it's a little tricky. Like to understand the exact asymptotics, there's like infinitely many different formulas. There's like one formula if k is smaller than root n, which is this one. And then there's a formula that's accurate if k is between root n and n to the 2/3. And another one if k is between n to the 2/3 and n to the 3/4. And another one if k is between n to the 3/4 and n to the 4/5. And so on and so forth. These don't come up too often. If you really need them, they're in this book. Well, one place to find them is in this book, Asymptopia by Spencer, which I mentioned last time. So if you want to find out really many more details in your life about asymptotically approximating binomial coefficients, you can check it out there. I'm going to kind of skip this intermediate regime and end in the last, 25 minutes by discussing good bounds when k is proportional to n. OK. But, as I said, I'm going to do that at the end. And I want to show you a few more bounds for n choose k, which are simple. And actually, these simple bounds I show you are going to have the property that they hold for all n and all k. There's no like, is k big, is k small? They hold for all n and all k. The only catch is they're not like super accurate. But sometimes, a quick and dirty bound is all you need. So let's see. How can we get some very simple bounds for n choose k? OK. Well, we can start with this formula up there and do the most naive thing to get an upper bound. It's definitely at most n to the k over k factorial. That's always an upper bound from that formula up there. But we want some kind of lower bound. Now, if you recall, earlier in this class, remember I was even right here on the board. If you can read the faint chalk, it's still up here in your mind. We had this bound for n factorial that we got by looking at the Taylor series for e to the x, dropping all the terms except for the nth one, and then plugging in x equals n. And that bound was that, I'll write it with k instead of n. That bound was, from 30 minutes ago, k factorial is at least k to the k over e to the k. Well, it's kind of right there, except that bound ignored this term and this term. It's pretty good, though. OK, so if you just plug this into this, you get that if I choose k is at most en over k to the k. And one great virtue of this bound is that this holds for all n, all k. There's no like blah, blah, blah about asymptotically how big or small k is. It's just always true. And this bound is pretty good. This bound is often like all you need in life. And it's great. I mean, it takes this thing that's got a very complicated definition and just gives you e to the k, n to the k, and k to the k. OK, so that's pretty good. We may like to get an equally simple lower bound. So let's do that by going back up to this formula and writing k factorial out as the product of k things. So n choose k is exactly equal to n minus 1, n minus 2, k terms down to k minus 1, k minus 2, also k terms. And you might say, like, OK, this part is n over k. The next part's like also almost like n over k. The next part's also almost like n over k. It's not quite, though. And you're like, is it working for me or against me? Well, I don't know what's for or against. But it turns out that, let me write it over here. But n minus I over k minus I is actually always at least n over k for all I. And I guess you can deduce that by cross-multiplying. This is true if and only if nk minus ik is greater than or equal to nk minus in, which is true if and only if I times n is greater than or equal to I times k, which it is, because we're assuming n is at least k. So what this is saying is that each of these factors here is at least n over k, and so therefore this is at least n over k to the k. OK, and that's a very pleasant lower bound that also holds for all n and all k. And it looks pretty similar to the upper bound. I mean, you see they're exactly the same up to a factor of e to the k, which is really often not that big, since if you think of k as kind of small, this whole thing is like n to the k. Like if k is like 10, these are both like n to the 10. It's just squibbling over the constant factor. Is it e to the 10 or whatever? So these are great like upper and lower bounds to just use in your life. And often they're going to be good enough. Let me, in fact, end this little elementary segment by taking the log of everything. So let me take the log of n choose k. And OK, I'll take the log of this for my lower bound. It's at least k times ln n over k. And it's at least, or sorry, it's at most k times ln en over k. OK, and I guess I can write this as k ln n over k plus k ln e, also known as plus k. OK, so you can see it looks real great when you go through the log. So I mean, the log of this binomial coefficient is like very close to k times ln n over k. It's off just by like an additive k. And it's interesting, actually, to imagine two cases here. Imagine you do k to be n to the 0.99. So ln of n choose n to the 0.99. Well, it's like you plug n to the 0.99 in here. This ratio is n to the 0.01. Log of n to the constant is like constant log n. So this is theta of n to the 0.99 log n. On the other hand, if you plug in, let's say, k to be 0.1n, so ln of n choose 0.1n. There, if k is 0.1n, then the n's cancel, and you get ln of 1 over 0.1, you get ln 10. You get, anyway, you get a constant. So you get a constant here and a constant there, and k just remains 0.1n. So you get a constant times n. Okay, and this is a general persist. If you have n choose like n to a power, it's sort of asymptotically like n to the k. But that stops when k is linear in n. You know, n choose something that's linear in n is just exponential in n. This log factor goes away. Okay. So, we're almost at the part where we're like, well, enough messing around. Let's just plug Stirling's formula in and see what happens. But I'll keep delaying that for one more elementary bound. And now, for this mindset, well, let me first say a couple things. First, as I mentioned before, n choose k, it's the same as n choose n minus k. It's like symmetric when you subtract the bottom guy from the top guy, which means that if you want to understand this, basically without loss of generality, you can assume k is at most n over 2. Okay, if you ever have to evaluate n choose k where k is bigger than n over 2, then just swap k down to less than n over 2 by subtracting it from n. And in fact, as I said, I now want to end by focusing on the case where k is proportional to n. So I'm going to introduce a new letter, p, and I'm going to write k as p times n, where I want you to think of p as between 0 and a half. And strictly speaking, you don't have to think of p as a constant independent of n, like what I'm going to say is true for every p, but in your mind, think of p as like a constant, like 0.1 or 0.4 or 0.5 or something like that. Okay, so what I'm saying here is I really want to focus the rest of this lecture on things like how can I understand n choose pn. For example, n choose 0.1n. So, okay, so we're interested in trying to understand this. And I'm going to tell you an elementary bound, and it's just going to be an upper bound. So we won't get a lower bound out of it, but we'll get what turns out to be an extremely accurate upper bound. And for this elementary ad hoc trick, I'm actually going to do you one better. I'm going to upper bound not only this, but actually this as well, plus n choose k minus 1, plus n choose 2, plus n choose 1, plus n choose 0. Honestly, I'm not giving you really that much more because the binomial coefficients as a function of k increase super rapidly. So like this thing is like almost always way bigger than this thing and this thing and this thing and this thing. So this whole sum is not much different from this last term, but anyway, we'll take this whole thing. And actually, let me give a name to this. You know how it ends. I'm going to call this v sub n k for this binomial sum. And this comes up a lot, this sum of binomial coefficients, because it's like the number of binary strings that have length n and at most k ones, Hamming weight at most k. And that's the sort of thing that, I don't know, comes up a lot in TCS. And so you may care to know how many such strings there are, or bound on such strings. This is also sometimes called the quote-unquote volume of the Hamming ball of radius k. Which is why I chose the letter V for it. Okay, so this is something that we may want to know an upper bound on. And I'll show you this ad hoc trick that works that's kind of similar to the way we bounded n factorial using the Taylor series for e to the x, except we're going to bound V using the binomial theorem. So I will recall for you the binomial theorem. Which says this, 1 plus x to the n is literally exactly equal to 1 plus n choose 1 x plus n choose 2 x squared plus plus n choose k x to the k plus plus n choose n x to the n. Okay, that's the binomial theorem. And let's assume x is non-negative. And in that case, actually, let's assume that x is between 0 and 1. Okay? So think of x as between 0 and 1. Mentally think of it as small. So actually, these powers of x are decreasing. X, x squared, x cubed, these are all getting smaller and smaller and smaller. So what I'm going to do to make a lower bound, first I'm going to drop all these terms at the end. I'm just going to drop them. They're positive, so not negative, so I can get rid of them. And then I'm just going to say, like, well, x, OK, this is really n choose 0, x to the 0. X to the 0 is at least x to the k, and x is at least x to the k, and x squared is at least x to the k. All the powers of x are greater than or equal to the smallest one, x to the k. So then we can change all these x powers to x to the k and factor it out, and we get x to the k. And what we're left with is, well, n choose 0 plus n choose 1 plus up to n choose k, which is this v n k. Everybody catch that? Great. So then we can just invert that and deduce that v n k is at most 1 plus x to the n over x to the k for any x that we want between 0 and 1. Think of n and k as fixed, and now like x is something that we can choose. It's similar to the thing with, again, where we bounded n factorial using the Taylor series for e to the x, and then we chose our favorite x. It's like mildly more annoying to figure out the best x to choose, but what we're going to just do is choose the best x that between 0 and 1 that makes this expression as small as possible. And get a good bound for the volume that way. So let me just facilitate that a little bit. This is 1 plus x to the n over x to the pn, because I'm calling k p times n. And that's good, because now we have two things that are to the power of n, so I can write it like this. 1 plus x over x to the p to the n. And yeah, that's it. So now we can choose our favorite x to try to make this not too big. And we'll get a bound that's like some number to the power of n. Well, you remember Stirling's formula. OK, so now there's a little calculus exercise to figure out what is the best x to choose. And I will either do it or not, depending on time. Let's not. OK, but just to recap. So we have v n k, or v n p n, if you will, is at most, I'm just going to expand this 1 plus x over x to the p out as x to the minus p plus x to the 1 minus p to the n for our favorite x between 0 and 1. And it's now also going to be convenient to write Q for 1 minus p. I know I'm introducing a lot of symbols, but I will. This is literally just the same as this, by the way. 1 plus x over x to the p. OK. So by the way, one reason for that is like, therefore, n choose k is n factorial over pn factorial qn factorial. OK, so I'm going to omit it, but calculus, because calculus, we have the best x, i.e. the one which minimizes this expression, miraculously, is x equals p over q. Actually, this is only true if p is at most a half. But we're assuming that. So in general, like if p is like 0.1 or something, this expression here happens to look like this. 1, 0, and this is p over q. If this is x to the minus p plus x to the q. OK, so that's a fact that you can check by plotting in calculus. If p is bigger than a half, the thing looks like this. So the best x is just 1, and you don't get a very good bound. OK, but this is at most 1, using the fact that p is at most a half, which is good, which means we are allowed to plug it in which case, so it looks a little gross, but something interesting is going to happen. With x, choosing x to be p over q, this expression in the base of the exponent, x to the minus p plus x to the 1 minus p, is, let's factor out x to the minus p, 1 plus x, OK, which is x to the minus p, 1 plus p over q by our choice of x being p over q. OK, and 1 is also known as q over q. And q plus p is 1. So if this is x to the minus p times 1 over q. And now I'll also remember that x is p over q. So I'm just doing some arithmetic in front of you here. So this thing is q over p to the minus p, well, I guess to the p, times 1 over q, which is 1 over p. This is the last step. 1 over p to the p times 1 over q to the q. Which is like an oddly enjoyable looking expression. So just I did arithmetic. This is what you get if you plug this choice of x into here. And therefore, we finally conclude this bound that I'm trying to get to, Vn Pn, is almost this numerical value, 1 over p to the p, 1 over q to the q, to the n. OK, and so if p is like literally a number, like 0.1, then you can like literally plug, and therefore q is 0.9, you like plug this into your calculator, you'll get some number like 1.83 or something. I just made that up. And so your bound will be like 1.83 to the n, which is pretty good. And actually, it's a bit of a sanity check. What if you take p to be a half? Then q is also a half. You're looking at n choose n over 2. Or actually, you're looking at the sum of all the binomial coefficients up to n choose n over 2. And you get square root of a half times square root of a half reciprocal. Anyway, you get the bound 2 to the n, which is true. All binomial coefficients are almost 2 to the n. But actually, that's a very good bound, because the sum of the first half of the binomial coefficients is half times 2 to the n. So it's actually a very accurate bound. So in general, this bound is going to always be at most 2 to the n, and it's going to be, in general, like some constant number to the n, and a pretty accurate one. In fact, we generally write this bound not like this, but as 2 to the log of this times n. And we call the log of this h2 of p times n. And h2 of p is literally the log of this number. It's called the binary entropy of p. And it's p log base 2 of 1 over p plus q log base 2 1 over q. And maybe you've seen it before. It's the entropy of a biased coin that comes up heads with probability p and tails with probability q. So it's a number between 0 and 1. Like if you plot it, it looks like this. That's a half. It's symmetric. That's 1. That's 0. That's p. This thing is 1. This is h2 of p. Okay, so this bound is, well, it ranges from it goes from 0 to 1, and it gives you a bound of some number to the power of n, which at the maximum when p is a half is 2 to the n. Okay, and one pleasant thing about this bound is there's like no like error terms or anything. Like this bound, some of these binomial coefficients is at most exactly 2 to the entropy of p times n with nothing else. Okay, well, we have just enough time to plug in Stirling. Looks like that's going to be horrifying, but it's going to be real quick. So let's do it. Oh, I want to keep those assumptions, which I just erased. So n choose Pn is n factorial over Pn factorial times Qn factorial. This is, remember, Q is 1 minus p. And now we use Stirling on all 3 terms, all 3 factorials. And so we get that this is asymptotic 2. In the numerator, we have good old Stirling, root 2 pi, root n, n to the n, over e to the n. Denominator, we have the same thing with Pn and also with Qn. Root Pn, Pn to the n over e to the Pn times root 2 pi, root Qn, Qn to the Qn over e to the Qn. Now let's see. Let's look at the powers of e. Pn plus Qn is n, so it cancels. That's good. Now let's look at the power of n. N to the, this should be Pn. We have n to the Pn, n to the Qn. That cancels with n to the n. So good. Okay. Some of the 2 pi's, root 2 pi's cancel. And what are we left with? So we are left with some constants, root 2 pi. And we got root p and root q. Those are all constants in our minds. And we get 1 over root n. So only one of the root n's canceled. And what are we left with? We're left with the exact same thing. We're left with good old 1 over p to the p, 1 over q to the q to the n. Oops. So this is the exact same thing as before. 1 over root 2 pi, root pq, 1 over root n times our entropy bound, 2 to the h of p n. Okay, so our upper bound was like miraculously close. It was only off by a factor of 1 over root n. And this is exactly asymptotically accurate for every constant p and q. And the last thing I want to say is look at the very special case when p is a half. So q is also a half. And this gives us the exact asymptotics of n, choose n over 2. And if you just plug it in here, you get that this is asymptotic to root 2 over pi, 1 over root n, times 2 to the n. And if you divide both sides by 2 to the n, you get this. And what is this? This is the probability if you flip n coins that exactly half of them are heads. And this is the last fact I'm going to end on. I want you to remember, because it's a good fact in life. If you flip n coins, what's the probability that they come up half heads, half tails? It's asymptotic to 1 over root n. Always remember this. The constant factor, we'll see why this constant factor arises when we look at Gaussians next time. But the main thing to remember is that this odd event, exactly half heads, half tails, has probability proportional to 1 over root n. OK, I'll see you on Thursday.